Okay, hi Thịnh. All right. Okay. Good morning, Professor Thịnh and everybody. I think we will start like in a couple minutes, but I would like to start next time. Like we try to start at 8, so not to waste time for everybody then. But this time, because I didn't inform you beforehand, so today we wait a couple more minutes. So next time I will start at, I try to make it at 8. And Professor, then if you have a meeting to do, and I think yeah, you can go. Thank you very much. All right. Okay, let me share it first. Yeah. Yeah. Okay, somebody tell me that you hear me and you see the what I'm sharing. Just one is enough. Okay, thank you. All right, I think last time, I think Professor Tan asked me about the references. So I would like to present this one first before we get into the chapter 2. So the EDA flow, yeah, the EDA flow, basically there are 3 main component of that. One is a logic synthesis, one is a physical design, and one is about verification. And in that, we can use a simulation to verify the circuit, the design, and there's also like that's the main thing. In each of that component, there will be the sub tool or sub topic. But let's get into the major topic first. So I think the first one in the EDA flow, which is I think what we try to. I think I covered that like briefly last time. The EDA flow comes from the beginning from the fab, which is the device design and also the technology design. And then it go into like a system, RTL, and go down all the way to the foundry. Our part would be from the when the foundry hand off the technology information, like the cell library, and also the device information. From that part, we will design our system and go down to the RTL and so on. So in that, the very first step in that flow is the logic synthesis, which is this part. The second step is and in that we have also the physical design, right? So this book, Logic Synthesis, is like dated in it looks like outdated, but the main thing is still not. The reason for that is that logic synthesis was mature quite a 10 or maybe 20, 50 years ago. What is new now for the logic synthesis is about like the combination from logic synthesis with the physical design. So this book, Logic Synthesis by Devadas and Cursor, these two guys is quite like a classic book about logic synthesis. In this, it will present you, it will like give you every algorithm for the logic synthesis, every step in that, which is from like when you get, right, from the RTL, you got a Boolean equation. Then there will be the algorithm to minimize it. So first of all, minimize the equation, the Boolean equation. The second would be to factorization. The factorization, which is you remember like the simple one, like xy plus xz. You can have it as an x factor with y plus z. That's a simple example. But in this, the factorization will be dealing with the very complicated, very complex Boolean equation, and then they have to optimize that. The input would be like 1,000 of inputs, and then you have you can imagine that a system of billion transistors. So the factorization or minimization is very complicated. So that is like, however, those things is quite mature. And after they factorize that and then optimize the equation, that's a 3-step in the logic synthesis, the main thing. So after that, they will do the mapping. So they map those equations into the cell library, which is in the NAND, NOR gate, the adder, the memory, and so on. That's all will be covered in the logic synthesis book here. But again, this one is a very like interesting for the computer engineering like guys, not for the electronic guys. Because in here, they will have to write the algorithm, they will have to write the program, the code to optimize that's called like an EDA tool. So that's what Synopsys and Cadence or Mental Graphics are doing. The second book is about algorithm for the VLSI, physical design automation. You can see that it's a physical design, which is this one, you have all algorithm about this. So what's in the physical design? So in physical design, we have a lot of steps in that. I think I will like add into the in the slides you got from I think the e-learning website. You might not get much about for it's called like a layout design, but you can see that the book is a physical design. So in that, there's the first one is that you have to do the floor plan, you have to do the placement, and you have to do the CTS, which is a clock tree synthesis, which is a very like a basic and then fundamental of the physical design. And later you have to do the routing and post-route, which is optimized after routing. And then you have to do another one is like to redo, to fix the whole time. All those kind of things here is related in the physical design, which is like all those optimization, like all those things here is done dealing with the real silicon or like real like layout. So all the algorithm will be here. So these the first two books are very interesting for people in the like computer science or computer engineering who want to get into the industry of writing the code to like to do the logic synthesis or to do the physical design. These two are not for people like using the software. Like you do the lab of like the lab for like logic synthesis, you will do that in the lab. Those lab is using, not writing the code. You write the code actually, but you write that code is the code to use the tool, not you write the tool for people to use it. So these two books, that's very, yeah, if anybody curious and want to know about that, the two books is like a classic book. Again, I think in 1994, recently, they don't do the textbook anymore for this because all those like about like when they do the synthesis, including combined with the physical design in mind, they do that like in-house and it become like secret. So it become like when the EDA tool vendor like a Synopsys or Cadence working with the chip designer with the like the design house, like with Qualcomm and Apple, or like everybody like who design the chip, they will get feedback. So the guy like us who do the design, we have something here and there, we found, okay, it need to do this way, need to do that way, and our design is specific. Our design has like some requirement, some demand, so the tool need to be updated to deal with that. So those things, they will work with the chip designer to improve that, and all those new algorithms to combine with the physical design, or like with like the real demand, actually, the reality. Those things, they just incorporated in the tool without announcing or without like publishing, because those things is kind of become like the secret in the tool. So they just will announce, I do that, I do this, but no algorithm will be announced. Only the algorithm will be announced from the university. But university now, the focus of they no longer focus on logic synthesis, because now it need to be deal with the designer. So, but they don't have that connection with the designer. They don't do the design, the university. So because of it, in the old day, the logic synthesis is alone. So that's why the university get a lot like involved in the logic synthesis. But nowadays it's not. Okay, enough for the two. The number three, the book number three is the quite a good book. Is include everything from synthesis, verification, and test. And also like I think they don't have much of the physical design, but I think that physical design, I think still I will introduce that in something else. But you can refer to the number two here. So this is the third book. Is that it's very good book that we can have. They present also algorithm. All these things is because you see that electronic design automation. When you see this thing, it means that like they talk about algorithm. They don't talk about how to use it. So we have the algorithm in synthesis, in verification, in test. But anyway, it has a good introduction about what is a verification, what to do, what kind of verification, what kind of test, what need to be done, and what tool, and so on. So it's really very good introduction to those topics. The number 4, 5, 6 is about like a HL, Verilog. So that's kind of give you the example for the Verilog. Verilog example for like some like a simple design, so that you can get used to that. I think you guys have a class of VHDL or like HDL. I don't know what kind of level that you have, but these 3 books is very good for that. It can give you like the kind of the starting point, give you some kickoff, so you can get used to that. Those like number 7 to number 12 here is about like the digital design, especially number 9, fundamentals of semiconductor fabrication. This one is about how they make the chip in the foundry. So those things is a very like specific. I just like I had a course here, it's like a long time ago. However, I think it's like evolve like a lot. Now there's a lot of pain. It's 2004, and now I think for sure it's in 2004. The foundry may mainly deal with the MOSFETs, the MOS. But from like 2010 and further, like later, they deal with they have like they started with the FinFET, and recently they started they research on like after FinFET. I will have the slides. Yeah, you have the slides after that. After MOSFET, there will be FinFET, and after FinFET, there will be something else. I will present that later today. So I think number 7A and 10, 11, 12, those things is about digital design. Basically, it's based on CMOS. You can, I think those things is a basic thing. So all these things is about like they will present the logic gate, logic cell, the memory, adder, multiplexer, and so on. So those things you guys learn in, I think, the digital design. I think that's what I was told. So I guess like you have idea about what I'm talking about here. All right, so that's about the references. So we, yeah, those things, I don't know how you can get a hand on this, because those books, I don't know if you can buy the books from Vietnam, but those book, if you have a chance, I think, by the way, I think sometime when I have a chance to go, like to visit Vietnam, I will bring those books home. And I think I will like give some of them to the library, so you guys can have some, yeah, maybe. For sure, I think from the 7, I think I have the number 11, and also I have some of like a 4, 5, 6, and then up to number 12. Those things I can print home and I can give that to the library. All right, so
You didn't turn on your mic, sir. You didn't turn on your mic.
okay, I'm sorry. Okay, thank you. And I think this, let me see, maybe this. Okay, so this chapter is about there are two main topic in here, even though we have 4, but 2 main topic. One is about the MOS, and one about the portion of logic gate on silicon. That one, I think, again, I would defer that to like what we learned before, so I can save us time. And the second part is about the electronic signal and electronic signal, the problem with electronic signal, which is the signal integrity. So the first thing is about how come it's not moving? Okay, let me make this sharing. Okay, this. Come on, what is this? I'm sorry again. I think my part is something some glitch here. Yeah, okay. I think now I share again, but I don't know why it's kicking me out. All right. Okay, just keep this way. I think this thing is the basic, right? So we have the MOS transistor, which is a metal oxide semiconductor. So we have a metal oxide and semiconductor, which is here. Here's a metal. You have this a transistor. So metal, and between the gate and the substrate here, you have the oxide, and then here's a semiconductor, to be brief. Sure, it's not like that simple, but to be brief, that's what they call MOS. Bipolar transistor. So using this, and then for the power thing, because the MOS transistor, the purpose of that is for the low leakage, low power consumption. But when you have like you need to like do the power amplifier or something like need the power, then you cannot use not you cannot use. Now they have like the MOS to do the power too, but still like not as good as the bipolar transistor. Then you have those discrete devices like diode, resistors, capacitor, and so on. What is a semiconductor? By itself, right? It can say like semiconductor, so half conducting. So you have a conductor is a what conduct, right? What is conductive? The other one is the insulator. In between is the semiconductor. So that's what we talk about, like the semiconductor does at the regular, like a normal condition, which is room temperature, and then the regular like a pressure and so on. However, when they introduce the purity, the like some like the dope or like some introduce the impurity, like another element into the semiconductor crystal, that semiconductor will become really like even like conductive in some source. Or when the temperature is rising, then the electrons will be moving faster or like have more energy. They can break from the crystal and become like the material can become conductive too. So in this so conductor, you know that like copper, aluminum, like those kind of things like conduct. The semiconductor is a silicon, germanium, gallium, arsenate, I think, and also insulator. You have SiO2, SiN, nitride. No. Those thing is this thing is insulator. So you have a conductors on this. It's like in terms of, I think this thing is in terms of rho is in terms of resistivity. So conductor has the least resistivity, and insulator has the most. Semiconductor fall in between. So this one they talk is about like intrinsic. Now they have an extrinsic when we introduce the impurities. When introduce impurity, if the impurity has like okay, the silicon has 4 electrons around the atom, and in the crystal it would be perfect to connect like this, right? So 4 and then it just like you have like a perfect crystal. 4 like there are 4 here, 1 2 3 4. The next one we have, so in the crystal it has like so we have a no electron like redundant. So the crystal is supposed to be like no conductive. That's why like we have the silicon. But when you introduce the something like the bore, right? Bore, no, actually bore is this one is phosphor. When we introduce the phosphor, there will be like there will be 5 electrons around the phosphor element atom here. So there will be 1 extra. That extra, they didn't show it here. So I think those like 1 extra around here. So this electron extra here, free from the lattice, free from the matrix. So it will like can move around. It has a more like a freedom to move around. It become the conduct like it gives the lattice some sort of conductive. So that one is like when you have the time of conduction is electron is called n time, and when it's like the hole, what is the hole? When you have like the impurity introduced into the lattice is like a boron, and this one has only 3 electrons around the atom. Then you see that here's this one is like it has like 1 hole in here because in lattice there will be 1 hole here because there's not enough electron to fill it in. Then when you have a field, like electric field applied to the lattice, so the one of the electron here, let's say like the electron here, one of them might have like the higher energy, and it will be broken from the lattice. It go out, but when it go out, it will fall back into when it lose the energy, it will fall back into this hole. It's as if you have the hole move from left to right, right? No, right to left, sorry. The electron move from here to here. It means that the hole, like now, it causes a hole here. So that means it looks like that the hole moved from right to left. So this kind of thing, they call like the whole movement like that. They call that like the p times silicon. So we have but think about that, like you can see that they call that the n time. This there's the feature is called like to characterize the n time of p time semiconductor. It's called mobility. So the mobility is the capability of moving around of the electron or hole. So you see that the electron has a more mobility than the hole. So you can see that later here. Here you can have the mobility here. The silicon. There's be some. Okay, maybe later. I think it's all right. So, so what I'm talking about just talk about is the extrinsic semiconductor, which is a semiconductor with the impurity. And when they introduce the impurity, it's called dot. All right, so P and N. This one, I think is not much. Yeah, it's just like you have when you have like a metal and oxide, and similarly is MOS, right? Yeah, when you have a tool like that, it becomes a capacitance. So the semiconductor here act like another electrode for the capacitor. This one is used in the, I think that you make a MOS cap, immerse a cap in the IC. Instead, we have the chemical like a capacitor in the PCB. This one is the time of MOS capacitor. They will do like something else, but the principle, the concept is this. Okay, this one is okay. Now this one I will introduce you, explain a little bit about this, but we won't go into the detail of the equation and stuff because not needed. This one, I think the one that you need to remember from like the MOSFET structure is that they have 3 electrodes: the gate, the source, and the drain. We have the substrate here. This one is the N transistor, right? We have a substrate. Then we have this one. Then we have this one is the simple description of an N MOSFET. In reality, there will be the something else here, like the N well stuff, but here they present like a simple thing, so that you can like get a concept about that. So we have this one N transistor. It means like the N, the drain and source here is an N plus. Then you have in between, like the distance between these two is called like a gate length, which is a L. This gate length here, and the gate here, they will apply the voltage here. They have a voltage applied to like these two. So the source electrode usually has the lower voltage than the drain. But these two, you see, these two region is doped the same way. So that means that it can be used swappable. It can be swappable for the purpose of electric connection. And you have that is like this one is width. See, it's width. So the MOSFET transistor has like a 2D and then the gate is a 3 thing. So you have a gate length here. That's what like I refer to. You remember when we said like the technology of 4, 5 nanometer or 10 nanometer something. Those nanometer means this gate length. It means that the gate length, the distance between these two regions. Okay, we go further and then I will explain. Okay, this one is said that N plus a low resistive electrode. Not okay. This one is okay. I think it's not really like your focus here, but I need to explain a little bit. The N plus here, they dope more, like just like to say that like the N time and dope more than normal, but not really low resistive electrode. The electrodes up here, when the pins go up here, there will be, because you have two things, right? You need the electrode to get like to connect to this region, so that electrode will be low resistivity. But this region by itself is not as low resistive because it is still like a silicon with impurity. Like it's still like a semiconductor region. All right. Now for the N. So for the N, you see that gate, source, drain, and this one you see that this one is, let's say, like 1.2 volt. This one is 0 volt to the, and then like you have a substrate connect to the ground. Here's the the charge of the current, the IDS versus the VGS. VGS and IDS go from D to S. So this one is a very like a small current, very like low current. When the VGS, when we apply the current here, right? Okay, let's start from the beginning. When you have the gate, the voltage applied to the gate here is 0. Is 0. So which means there's no bias in the circuit, only the D. You have the VDD here, which means like you have only like that. Then from here to here you have normally you have I think this. Where is it? Okay. Sorry. Okay, let's go that. Okay. When you have a no voltage applied to the gate, it means a no electric field from here to the substrate. Then the current, you see that the current is almost 0 here. Also, because in here there's not much. In this here there's not much of like electron or like a free electron to conduct. So whatever like left, whatever like whatever electron exists in the lattice, it moves, and then it can like cause like the current from here to here, right? So the electron move from here to here, and then the current like because they're positive, it go from D to S. Electron move from the left to right, and then the current move from right to left. Because only like the free the free movement, so it's a very little electron to move away, which is the current is very low. Until like you apply that into a certain like a threshold voltage, this one won't have any effect, or like very low value. That's why I call like this one. And then like just like you have a threshold voltage until that, when the voltage here is like achieve a certain value, then the current start to like move up, right? So in this one we can like have remember two things. One is the subthreshold region, and then one is the leakage current. The current when there's no voltage applied to the gate is called leakage current or subthreshold current. And then when you have like when it go up like that, this one is a linear. So this one is like the current will increase with the gate voltage. So this one is the gate characteristic. Is that again? Yeah, gate characteristic. Now we go to like the yeah, okay, this one I just said. Yeah. So we have the leakage current, and then the VTH. The VTH, which is a V threshold here, right? So remember, VTH is when the gate voltage is lower than the threshold voltage, there's only leakage or subthreshold current. When it like above that, we go into like a normal or like a linear here. Like we have a strong inversion. Inversion talk about the region here related to the semiconductor stuff. Then I think there's some idea you have the threshold voltage is about 100 millivolt. But nowadays it's go down to about 50 millivolt. The reason for that is because they need to get the transistor go faster. The thing is that the speed is proportional to the current, right? The current, the higher the current, the higher speed. So when they want to get like the higher speed, they have to like get the current higher. To get the current higher, they have to dope. They have to dope this one, and then you have to dope this thing like more heavily, so that they have a more electron to go through than more current. But the more they dope here, it means that it's the more leakage, and also the threshold is even like lower, right? Because they dope more here, so it's very susceptible for the gate to turn on. So which is you have this one like now it's going down to about 50 millivolt or so. One of the reasons that the threshold voltage here go down is also because you can see that in the old days, I think in the old days like 10, 15 years ago, no, more than that, maybe 15, 20 years ago, the operational voltage applied to the VDD is about 3 volt. I think initially it's a 5 volt, you go down to 3.3 and go down to 1.5, and now about 1 volt. And they stop at 1 volt. And then now they can go to like a 700 millivolt. So you see that with 700 millivolt, and they need to have a higher speed. Again, I think one more thing. To have a higher speed, need higher current. And the current is proportional to the VDD, right? It's common sense, right? Common sense is you put like a higher voltage, you get higher current. Put it simple, if you call this one is the R, the resistance. So like the current is a voltage divided by resistance, right? So that means that the higher voltage, the higher current, the higher speed. But now the voltage is going down, scale down, because the voltage is limited by this metal oxide. When they get this one, again, okay, those things is like related to technology, but just like just keep in mind that. Then for the ID, here's the leakage is the order of nanoamp, and nowadays they can keep that down to like in the 100 picoamp. So as I said, it's like even they because they reduce the voltage, which is you have a less voltage, then you have a less leakage. It's contradict with what I just said, like we have to like dope like more, right? So that's something like going like opposite way here. One is you have to dope more impurity so that we can get high current. When we dope more impurity, that means the leakage is increased. But because you reduce the voltage applied to the drain, then the leakage is reduced. Then when they do that, like they have some like a process to make the current, like the leakage current, like a smaller. And then going forward with the FinFET, the leakage will go even like not will lower, because it's like they go opposite way. One is like we reduce voltage, leakage reduced, but we add the doping, then leakage increase. Those imbalance each other, and then like at the end we have the leakage like stay the same or even less. Okay, this thing you can like read and then understand. I don't think it need much explanation here. Yeah, this one just I said when the VG less than VTH, which is you have no current, and actually that's only leakage. And this one is a trend. They said like trend characteristic. It means the IDS. This IDS versus the VD. So you have that is a. I think just those things is just go to here. The reason I skip all these things and go directly to this formula, because this one is I would like you to remember for all kind of MOSFET summary. Because remember that when we do the design, all we care about, we have to always, okay, remember that we have to keep in mind always that PPAS, performance, power, area, and cost. So the first thing to achieve is performance. It doesn't matter if you have a low power or not, but if you don't achieve the performance required by the customer, your product won't be bought. They won't buy your products. So that's first thing. And the next thing is that when you achieve the performance, then you try to reduce the power, because you cannot like burn your circuit, right? It's just like the competitor can do the same performance but less power, then they will beat us. So we need to like care about the power, because remember, like for things like in the cell phone, the power consumption, maximum power consumption for the chip need to be less than 5 watt, because when you put a chip in the cell phone, you don't have a fan to like to reduce the heat, to like to conduct the heat out of the cell phone. It will have to like the heat will be escaped by itself or by the heat sink. And they calculate that like 5 watt is the maximum that the chip can escape the heat can outside by itself, by the heat sink. So because of it, you have a power budget. So that's the second thing. And the third one is about area and cost. Those things is like we will talk about it later. But here is why I talk about the performance power here, because in this one, it will like performance is always related to current. The higher current, the better performance. That's the key thing. So remember that. The second is higher the current means higher power. So the power, higher current is a higher power. So I think I will explain to you like so you have a sweet spot between the two. However, like a view from simply like that is very contradicted. However, these two are not really like tied to each other. I will explain to you later. But first of all, we need to understand what the current depends on. So the current depends in this, right? You have in the saturated region is where, okay, here's the drain characteristic, right? The drain current. So you have that like on the right is the saturation, and on the left is the linear region. And basically, the transistor or the circuit operating in this one or this. Here is when it switch the status from 0 to 1 or 1 to 0. So most of the time will be here or will be here. Then you see that when it will be here, you see that it's like a saturation region. When the VD, like the normal one, the ID will be like proportional to square of the VG, right? Square of VG. That's first thing. Then you have and when you have like in the linear, it will like it will, because in the linear you have VDD, right? VDD is constant in the circuit. In the device, when you have a chip in the board, it will be like 1 volt or something. That voltage is constant. Because it's constant, so I think in this one you have this one. Basically, it depends on the VG, so it's linear. That's why I call like IDS and the linear. Then you have a factor beta n. Here is the very like important factor, because this factor design, you have this thing is designed by the voltage, but the beta n here depends on the design and the technology. So what is the depends on the so you have here beta n. So the beta n is to have the mu is the electron mobility. That's what I talk about, right? The electron mobility. But this one actually, I think electron or like I think it's supposed to be like electron mobilities or like the whole mobility. And then like for the electron, I think it's about like 2.5 times of the whole, about the mobility. So because of it, you see that like for the P transistor is the current, you see that is proportional directly linearly. So if the mu is 2.5 times bigger than the n mu, right? The mu n is 2.5 times like a big of the P time. It means that the current will be 2.5 times. It also means that the speed will be 2.5 times of the P. So to make up for that, they will have to make the P transistor usually 2.5 times bigger than the N transistor, so that they can balance the current when it switch, when the N transistor turn on or when the P transistor turn on. This in mu and Cox. This one comes from the technology, so we cannot do much as a designer. Also the L here and TH. So the gate length, right? You have a gate length in the denominator, right? So that means the gate length is the smaller the gate length, the bigger beta n, or the bigger current, or the higher speed. So, but this thing is like this one is from Faraday. We cannot do much. The one we can affect is the width. That's how like the cell library will design, and then they will change the width to have a bigger transistor, to have the speed as they want. So I think remember from here, right? Remember again, like what we depends on, what we need to do to increase the current is we increase the width. And then when like because understand about the mu, the mobility, so that when we design, not way, the cell designer design, they will have to design the P transistor bigger than the N transistor, so that the CMOS have a balanced outcome, balanced voltage, or balanced current actually. Yep. Okay. So this one and operation of NMOS transistor. Yeah, I think we have that already. That's fine. PMOS. For the PMOS, you just like take the absolute value of the NMOS and you have the same. But only one, you see that beta is a beta P here. The beta P here is about like the beta N is about 2.5 times of beta P. And when we have a CMOS transistor like this, you see, I think we have that like next one here, but I can explain from here. So to make here's the inverter, right? Here's the inverter. So you have when it's a 0 here. So this one 0, which is this one will turn on. So you have a current go out here. So you got like a VDD here. So you got the logic one at the outside, at the output. When this one go to 1, then this one turn on, right? This one turn on, the charge from here will be discharged to this N transistor here. It's a P. You can see that this N, this is a P transistor, right? You have current charge to C load here. And when this one is turned on, so it's this. You want that like the current here and the current here will be the same. So that like it charged here, it charged to the C here, and it discharge here will be the same time, will be the same amount of time. However, because the N is faster, right? If you design these two with the same size, same width, then this one will be charged in here is slow down, like when this one discharged here. So yeah, that's this one, I think. That is simple one here. This one, this is a logic gate. I think you learn already from like I think digital design. We have a nano and AOI. This one is called combination gate. This kind of thing, and we call that like in like you can see like the name of the logic gate in terms of combinational equation. If you have a AOI, it means like you have an AND gate first, and then you have the OR and then you have an inverter at the output. If you have an AO only, it will be A and N and O. If you have like a OA, it will be O and A, and so on. So that will be like when you look at the name, you can like derive the functions of the logic gate. So the way yeah, I think this one is a simple. You have a NAND here, so that means a NAND 2, right? The NAND means like it turn on only when the two inputs have the high value. So this one, you have a 1 and 1 here, it turn on, right? Or both of them turn on, which is like it's short here. You have like this one will be like a tied down to 0, which is like 1 1, and the output is 0. So either of the input is 0, which means that the transistor will be off, and the transistors will be off here. But either of input is 0, it means like one of these two transistors will be on, and it's on, which means like the VDD here will be short to the output, which could provide the output of logic of 1, similar to the OR gate here, the NOR gate here. Sorry. Rosin, I think is the flip-flop here is the same. I think you can like oh, there's one thing is need to be, I don't know if let's say yeah, this one I think you can see how it works. Oh, setup time. I think maybe I missed that the last time. There's a two concept here when we go to the flip-flop. So when we do the flip-flop, we have the input, data input, and the clock input. The clock input here, so that like it will launch the data into the circuit, so that it won't change after the clock, the edge. For example, here when we get, let's say the here, right? When you have a 0, the clock is a 0 here. The clock is a 0 here. So this will be like this one is a P transistor. When you have a 0, that means it's turned on. So the data from here go inside here. So data will go to this point. In the meantime, because the clock is 0 here, then you have here is 1, which is this one is off. So whatever like a data come from here, it go inside here, and then like you have this one is large. So you have a 0 here, it will be 1 here, and it turn back to here 0. So it keep like this one like intact. It cannot change. When you have 0, it cannot change. So it keep like and then 0 here, and it become 1 here. Yeah, it can become 1 here. Okay, here is 1. Sorry. And this one is like you have a 1 here, so this one's off. So that means whatever data here, it will go out here. So it is isolated from the input, right? This one is whatever it's here. Before it was whatever is here. Now the thing is a setup time. When the tricky thing is when you have this D input here change at the same time as the clock, right? So if the D input is changed at the same time here, so you have the clock here. Let's say here the clock here. Let's see, I go from here down here. This one is up, this one is 0, so it should go in here. And then when it go like down to 0 here, right? And then when you go up, now I say like at the beginning, it go up to 1. At the beginning, it go up to 1. It means that the value is going here. When it go up to 1, it means that whatever data here is stay. The things outside here cannot go inside anymore, right? So you have that here, and then this one open, so the data from here it go out all the way here. It will like provide the data from here will go out. So you have that's why they set that like the output, the thing here at the positive edge here, the data will be get out here. Okay, but the point is here I want to explain is about the setup time and hold time. Setup time is the data need to be stable at least before the edge, the clock edge, so that like it need to be stable, because you can see that clock here, right? if like what happened when we have a data here happen at the same time as the clock. So this one is when it should turn on, it go up like that. This one also like go up. So this one go up. So that means like in the meantime, you don't know, we don't know this gate, this transistor will turn on, but it doesn't know which value to like go from here to here, because we turn. It's uncertainty here, because it doesn't know if the D value is a 0 or 1, because it's in the time of transition. So it doesn't know. So that's why it cannot latch the value here to here. So this one is doesn't know. That's why we need that like we need the data here, D, need to be available like at least a certain amount of time before the edge. Let's say that before the so that I say I have a 0 here, it's stable. Then when I turn the clock here to 1 to cut it off, it knows that okay, now it's gone, and then now I have the data correct here, right? Actually, yeah. So the same thing is with the whole time. So after that, it need to be like have it. Okay, again, same thing. Whole time before. You need to understand like setup time is before the clock, and whole time is after the clock. The setup time. Okay, this thing is I don't know if I said that already. No. So the setup time here, there's a 2 times of setup time. You might be confused. So the setup time people talk about here is a setup time. The setup time for cell. The whole time is also whole time for cell. So remember this thing, these two things is the value for the cell, for the logic gate. You will see later on there will be another thing we people talk about. I think I already talked about like the setup time is the setup check-in. The setup timing is the related to the frequency or the target frequency, and the whole time is so remember here when we talk about this in the cell is the setup time for cell and the whole time for cell. There will be, remember, there will be setup time for the part for the design. That one will be different from this. So along the way when I go there I will explain that. But for now you know that it's only setup time for the cells. Yeah, okay, that's what I just like explained. Like here's the metastable state. When if the V in here is in the middle like that, it like a the transition in the middle like that, there will be like a unpredictable status. Then the circuit won't work properly. So that means that they need to have like a status. The voltage need to be stable here or here, because in the middle like that, don't know what it is. SOC design and jigsaw puzzle. So this one, so as I talk about, right, the SOC system on the chip, which is we put multiple blocks in the same chip. So the multiple block, I think the total block, it need to be rectangle, because that's the one we put in the chip, and then like we can cut that, right? We can cut that in the wafer, silicon wafer. You can cut that into like the rectangles, but inside is that this one is the shape of the chip, but the block will be like as the puzzle, because of like each block will be designed in a way that like fit the requirement, and then they can go to like this shape like that. So the process to go to like negotiate those things is a long process. It take like a month, like 2-3 months for each time, for each new cycle design. So for each like that, yeah. Just like to explain why it's like we have the jigsaw puzzle or like the puzzle. So it's not like a small like that. It's not the same thing either, but it's like the shape, as I said. This one is about 7 blocks, in the reality there may be like really 100, but it's like it's not the same size. Each block is not the same size. Some block is only like small like this, or like it's even small like this. It depends on the blocks. Circuit library on SOC. Those things I think you can read by yourself, right? There's not much to talk about. It's just the analog circuit. Yeah, we have this thing is what we have to deal with, and in this one you have only this POL is it is the analog circuit, but we need that because this POL will be used to generate the clock for our design. So that's why, like in our design, we will have the POL. But those are I/O. I/O here is the input-output buffer level shifter. Those things will be at the level of the chip level, which is you see that the name I/O will be input and output buffer. Before, like our design is inside, right? So it needs to communicate with the outside world, which is it needs the buffer. And those buffer is special because it's not the same buffer as we do that here. Because in the side, we don't have the ESD electronic, like a static thing. Because when you remember, like in the world, there will be the static electric that can shock the circuit. So they need some I/O to prevent that. So there will be the protection in those I/O buffer. These two things. In the input-output buffer here, there will be like a protection, and there's also like a buffer. Because it go out inside, the current will be small, but when you go inside, it will be like it will try maybe like the PCB, right? The PCB has a big metal layer, so the capacitance will be higher, so the current will be higher. So it need like a stronger transistor or stronger buffer. That's why we have the input-output, the output buffer, and the output buffer also will write like that. They will have the protection circuit to protect it from damage from outside, and then the input, so that like you can like in the input you can have the protection too, and then also like will convert the voltage, because the outside can be it go from like the circuit of 3 volt to the circuit of 2 volts or like 1 volt. So that's the I/O. But those things I think is at the chip level, like at a very high level. What we deal with usually is a block level. So in that, when we communicate between this, it's just like the regular buffer. There will be the usually like the terminal, right? The pins of the SOC. This thing will be actually I think this one is in the old days with the wire bond. Nowadays the thing is like this. The SOC, and then the pin will be like this. You see that it's like if you guys buy the Intel like a processor, you can see that, right? Or like that. So the pins in the middle like that. But as it's pin like that, there is an input. You have the input buffer. Output, you have the output buffer, and then you have Then you have this thing is analog. Those in analog. So from this portion, it's about the electronic signal, which is related to like some we need to understand something about the electronic signal so that we can understand about the signal integrity. Those things we have to satisfy the requirement of the signal integrity so that the circuit can function properly. I think we have okay, let's take like a 5 minutes break, and I think I will give some more about the advanced technology for the FinFET and after FinFET after the break. So we can take a break now until 8:10. Sorry, 9:10. Okay, I think it's let's see what I. Yeah, okay. All right. So MOSFET that we talk about, it was established. It was like mature a long time ago. I think about maybe 10 years ago. And then because the limit of the MOSFET is I think it's all drive okay. What drive the technology is about the current, the high speed. So again, PPAS, power performance power. So the MOSFET is that kind of like run its course, which is it has now it has it cannot have the higher speed, which is because they cannot provide the higher current because of it. And then also if they want to do higher current, then they have a problem with the leakage. The leakage should be higher, so they have to resort to something else. So since 10 years ago, I think they start with like, I think the 20 nanometer or something, it has the FinFET. So the FinFET, you can see that from here. You can see that from here is like the traditional planar, which is the MOSFET. So it's like you have the gate here, and you have a source and drain. So the source drain, the current go this way, and you have the width here, right? And the gate length. So you can see that, what is the, okay, you can see that the electric field applied to the gate here is just on the surface. So it's just go from here to the, here, this small one here, you go to here. Now, when you do that like this, you have, you elevate, you raise you raise the source and the drain up, so that you can have the gate like embrace the source and the drain, then the what is that? You can remove this presentation. Okay. So you can this one. Okay, so when we do like a tree, you can see that the voltage now apply. This one is the source, the drain here, right? And then the channel here is right here. So you can see that if you do that like 3D like that, you have a three-way that the voltage can apply, can like have the effect on the channel. And common sense, because of it, the current will be like can be higher. Now the current could be higher, but because now, and also like this one, because it's like it's a three-way like impact, which means that when you want to turn off the current, it will be like even like much better, because you have a like here you have only like one way, like the field, the electric field go from here and go down. Here it go directly. So you see that this one is go directly to the channel, which is a more effect. That's why it has a less lower leakage. It has lower leakage. And then also like it has like the IV current get flatter. When it get flatter, which means that when okay, I think yeah, the current get flatter, which is the lower dynamic power consumption. I will go there to back to that to explain. So the FinFET here has all kind of things that we want, which is a higher current, higher performance, lower leakage, and also lower dynamic power. So, and also it's a scale better, because you can see that when they do like this, which means you have the transistor is smaller, right? You see that this one they have transistor only this size. This one it need to be larger because of the width here. Now the width is depends on like the vertical one here. It's not the horizontal one here. So it then can be smaller. That's really like what we wanted. So it's like from like a 28 nanometer. They say 28, but actually I think it get into production about like a 20 nanometer and up until now. So the advantage of that, all thing, this one is for your reference, that you can read that to see like in more detail. But remember, the key thing here is with the FinFET is lower leakage, higher performance, lower dynamic power. That's all we want. And also like a lower area. So it's kind of a dream come true, right? Because it's like everything we need. So we have it. However, it runs its cost too. Because now it's go, when it go like it go to like it's go to down to like 4 nanometer. Remember this thing? Oh, sorry, this. Yeah, you have this one. No, I think this. This one. Where's that picture that I can show? Okay. Okay, I just go back to here. So this get length here, right? So when you have this one, you go to the FinFET. This one is like this get length here. That's from here to here. That's the get length. So the get length here, when it get very close, and then everything, and then now I think there will be like it reached a limit, right? You have a 3 nanometer. You have since it reached a limit. Now they have to like because you have only one like that. One like the gate is only one like this. You reach a limit, so they have to invent like something else to replace it. So the performance now is reached a limit. They have to introduce the gate all around GAAFET, which is like they have, instead of having like you have like the gate here is only three sides, right? One here, left, right, and top. This one you have that like all around, and then they have not only one like a region of like doping region. They have a 3 is assigned. So when they do that, you can imagine that like the current will be even higher, and because you have instead of 3, here's each region like that is equivalent to 1 transistor. If you can put 3 in the same time like that, then it means that you have 3 transistors like in parallel, which is increase the current, increase the performance. Then in this one, and you can see that because they put in vertical like that, it means that like the area that you have a higher performance, but you still have the same area, which met our requirement for the A, right, in PPAS. And with this one, it control, because it completely embraced the region, the channel. The channel is impressed by the gate. Then you have that the leakage will be controlled very well too. This one is the concept. In reality, they will do like an MBC FET here is by Samsung. Samsung do that as a nano sheet. So which is you have that like in like instead of just a wire like that, they have a sheet like that with the width can be like adjusted, can be like a tune. Yeah, like this. When you tune this one, the current will be like very continuously. For this one, they just like a jump like a quantum, right? It's a step, but this one is a continuous. So it gives some like flexibility in design. Yeah, this one is I would like to give you this picture so that you have some idea about design cost when they want to do a SOC. So this one is it's kind of average SOC for like the CPU or like a SOC from Qualcomm or Intel. So you can see that since like the 65 nanometer, let's say like when was it the time? 40 nanometer is about 2012. This one about 2010. Yeah, 2010 until here is about 10 years, 10 or 11 years. And you see the cost go from 24 million to 500 million. And with this like a trend, I think that the 4 nanometer that we are at right now is about 700 million. So with this, you can see that like with the cutting edge, you can see that like not many designer can do it. Only the big guy can do it. So the guys like they can only like do the old chip, the old node, so that to be like cheaper. And as I said, I think at the time I said like you see that software, the cost of like a chip in that the software almost a half. This one software, which means like we have the firmware, we have this. So everything here is really software, including like the cost of the EDA tool and so on. The cost. Physical is that much, but the verification, you can see that. Architecture, the design here, I think this one is they put that here, but I think it might be them because based on what I see, the cost of design in the logic synthesis is much more than that. It's not just this. You can see physical here and this one, right? The architecture here, But the architecture is so important that without this one, this thing is meaningless. Because the guy who decided, okay, the breakthrough or like the innovation, most of the innovations will be in this. Because they will design like what is the in, what is out, what need to be done, and so on. The physical here is just like doing it, implement that with the just implement that. So this one I think is supposed to be like a higher, like a bigger. Then you have the verification. The reason the cost of verification is high because it's very tedious. The guys need to understand about the circuit and need to like explore all the combination, or if they want to like optimize the coverage, right? Let's say like for the circuit, for the design, there's a billion of pattern. They cannot do it, so they have to optimize that and reduce the number of pattern to 1 million or like 100,000 or something. They have to like do that using the software to do it. So the verification is a two part of that, is a running time and also like also the knowledge of the circuit and a lot of things. That's why it takes a lot of time. Is costly. Physical, I think this part is like also costly too because of the it's also tedious because it's deal with the it's a lot of things like things in here. So you see that is okay for this. What we can do is here we have like a lot of like a bang for the buck. We can do a lot of innovation happen in the architecture. Verification search to make sure that like what we do here work properly. But innovation is here. This one also in here, but not as much as here. And there's one so like the combination or like the time or like the time between the physical here and the architecture here. Nowadays, this portion, two portion is not isolated. They are like in the same boat. So I think it is like yeah. Yeah. By the way, I think this to say that even the FinFET run its course, but still they have some like they are at the end of its life, which is the TSMC still stay with the FinFET for 3 nanometer. So this year or like with the with Samsung coming out the Galaxy S22 22, right? And it will have the 4 nanometer along with like Apple. That's a 4 nanometer. At the end of this year, I think maybe it's a 3 nanometer, and TSMC stay with the FinFET for 3 nanometer. But beyond that, I think it could be like the get all around FET, that which is we don't have much. We don't know much about that yet. I think always one thing is like when the foundry like a TSMC or Samsung announce about the new technology, it will take roughly 2 or 3 years for that to be implemented in the device, which is the prediction is the GAAFET, the GAAFET will be in the device 4 or 5 years from now. 3-4 years from now. But you know, there's a delay, right? They do that, they announce that, they like have to get it ready, and then the design have to like, okay, now I have the data, I have the technology, then I start to design on it, and then after I design it, I give back to the foundry, and the foundry like start to like produce. So it takes a while. It takes a while from the design, okay, from the beginning of this node until like it is implemented on the device. All right, so that will be done with the FinFET. So let me switch back to the, let me switch back to the class. Which is like the signal in the circuit. The signal on the left is the ideal wiring, which is in the old days we have the zero resistance, zero capacitance, and zero reactance, inductance. So with that, the circuit is like this, right? So if you have the cell here, you have this, whatever. So you can see that like in the old days, they just need to do the logic synthesis, which is dealing with the Boolean equation. That's enough. But the more and more you have now in the real world or like in real life, and then like going forward, because you see like when they scale the technology node to like a nanometer like that, the distance between the transistor will be closer. So which is supposed to be less resistant. However, because of the feature length is reduced, then you have the thickness and the width. Here is in the circuit, right? You have this one. Here's a Y, is the length, and here's the thickness. And this one is the width of the middle Y to connect to like let's say like here. And this one at the end here you have like the input of right, and this here you have the output of the inverter. This Y is shorter than before, but the thickness now is much like thinner than before. Let's say 5-10 times than before. The width here, because the width here, let's say that before we have the 40 nanometer node, then the width here is in the range of 100, like 50 to 100 nanometer, right? The implication of that is when you have this width is a bigger, then that means that the resistance of this one will be like lower. The resistivity will be lower. Now we have this one width go down to only like the width is only 10 nanometer, and the thickness is go down to in the same. It's about 10 nanometer too. So you have a two-way of like a reduction of 2 ways of the thickness and the width, which is like a double, right? Exponential. Which means now the resistance is very high, and then resistance increase. C increase too, because when you have this, which is you have the capacitance is proportional, like inversely proportional to the distance between the two electrodes, right? Which is in this case is the wire, and you have the coupling capacitance, which is you have one wire here, there's another wire is coming here, it is running in parallel, another wire run parallel here, so you have a cap here, that's another one. And then like you have the cap is like C, I think C proportional to like I think the width over I think the thickness outside, and also like width, thickness, and L with L. L here is for So you have the width is reduced, but the thickness is also reduced. So basically I think because this thing width reduced, thickness reduced. So in the real life, I see that we have the C per micron is almost constant, which is about 0.2, if I remember correctly, 0.2 femtofarad per micron. That's the number. That's kind of like the number. It's just stay the same for maybe 20 years. So the thing is now L, right? Which is the N. L decrease too, which is supposed to be we have a less capacitance. But the problem is now we have the distance between this. We have because before we have the two wire like far away, right? We have two wires about like 100 nanometer away. So that means that the coupling capacitance is small. Now the thing is like very close. Now we have a coupling capacitance now like dominate the total capacitance. Because of it, we have the C is also increased. You have an R increase, is increase. The L, which is inductance, this one basically is not an issue in the real life. The reason for that, for the L is not an issue, because L can become an issue with the two reasons. One is that the frequency is very high in the 4 or 5 gigahertz. And the second is that the length of the wire is long enough. We have the frequency go up to 4 or 5 gigahertz in the Intel chip, but the length, you see that is reduced. The length is like in the, you have, because of scaling, the length is reduced. The distance, the length, wire length is like the distance between one gate to another, right? So when you have the logic gate is smaller, they pack like more, then you can imagine that the wire length is smaller. Because of it, inductance is not an issue in the design. However, it is an issue in the package level. Because in the package level, you can observe that the package is almost the same, even regardless of the technology node. It's about like that size, like I think about 3 by 3 centimeter, something like that. The package is 3 by 3, which is if you see that it go from one corner to the other corner, is about like a 6. It's about 6. It's about 6 centimeter. Is a very long with the frequency of 5 gigahertz. So in that case, we have to do something like to deal with the inductance, but that's at a package level, not our design level. By the way, I mentioned the Elmore delay here. When you have the circuit like that, right? This one's a Y, right? This one is like when you go. This one is the model of the Y, so which is like the T model. You have the inductance, resistance C, the inductance, resistance C, and so on. So all these things, they will calculate. They use some like a Elmore delay. Like this one is a one method to calculate the equivalent circuit of this thing. So they will like reduce the whole thing here into like one like this. And because the L here is almost a 0 in this kind of thing, it's basically like this: R equivalent and C equivalent. So there will be many methods to calculate that. One of the things is in the academy literature is the Elmore delay. You can Google it to see what is the Elmore delay. Now the effect of R, C, and L. Okay, this one. So you have the R. Okay, L. I just talk about that. Now talk about R. The resistance, you can see that there's two impact. One is always you have resistance, then you have an IR drop, right? It's simple. But the IR drop here, there will be the difference. There will be like impact on the power grid and on the signal. For the power grid, it will reduce the power, the voltage on the terminal, on the pin of the logic gate. Let's say this one. This one is a logic gate, right? So this one is like the source of the voltage of the power grid, and because you have a resistance over here, so you have the IR drop, right? You have the current go through here, you have resistance, so you have the voltage drop on this resistance is voltage equal to current multiplied by resistance. So this one, that's called IR drop. So that means here, let's say you have a 1 volt here. After this, here becomes 0.8 volt. 0.8 volt, you see that is you have a 20% of reduction in voltage. It also means easily 20% or like even more, 30-40% decrease in performance. So that's why I think nobody want to have this like kind of resistant IR drop for the power grid. So for the, that's why like for the power grid, they try to make this resistance is like as minimum as possible by using the very thick layer, very wide wire to be able to connect from here to here is like with the lowest resistance. So that like so because of it, you can see that like in the later on you can see like they model the cell with the timing. They model that from like a 0. It go from, no, that's related to the okay. I talk about that's something else. So that's about the power grid. So the purpose about, because of that power grid, they have to reduce about the voltage, the IR drop. So they have to make the power grid very strong, which is with the very wide wire. But now for the signal, right? The signal, this is also the thing. The signal will go like with, you have a resistance, right? Resistance. So the current like a charge here through here and then charge to the load. When it charge like that, so it will go up, right? It go up, but it go up like slowly. The more resistance, it go up slowly. And the more like a resistance when it discharge to go to 0, like here. When it discharge, it will go like that. So you can see that if like the resistance is too much, and along with the capacitance, the FFC, the capacitance is high too, then it cannot discharge enough to get to 0. And then you go down. So the result, the consequence is you have this one is not really a signal from 0 to 1, but it's like something in the middle, which is it failed the requirement for this signal voltage. So it failed because here at this point, I don't know if it's 0 or 1. And then it's like go back to here and it go back to 1, right? But it means that like the signal seems to me like stay at 1 all the time, even like input is like this. So that's why for the signal it's a little bit different. It's not like require that wide like the power grid, but it still requires some sort of lower resistance. So what can they do? For the what can they do for the for the signal So for the signal with the resistance, if the signal is still like fast, and when they see like this, they have to reduce. They have to reduce the resistance by using some special rule, which is they said that like NDR. Okay, I use that so much now. I forgot what it stands for. So the thing is that they will have some design rule for the critical part. Let's say that this Y is as critical, right? I need that to get into here. So I will mark this one wider by making the width is a double or triple. But triple is the maximum that we usually have. Because if you make it the triple, it will take away the number of track of Y in the circuit, right? In the power plant like that, power grid like this, they can make it wider because there's nothing else for the power grid. This is the top layer. Usually the power grid is on the top layer and it is only for power grid, so they can use whatever they want. But here's like for the lower layers, it is used to routing to connect between the logic gate. It will be like crowded, so we cannot like make the Y as wide as we can. We just have the 2x or 3x maximum. So with that, we can reduce the width. Then we can like really like limit this one. Another way to reduce the resistance is we buffer it. But that go to the next thing is that when we have the long Y, we will buffer it. So the third one is the effect of L. I think I talked about that. And then it represents in the circuit signal by the bounce in here, the ring in here. When you have the circuit you simulate, we have the ring in here. That means there's an L. The ring in is L because it represent the resonance, right? When you have a circuit with L and C, That's a resonance. And you have that like a kind of go down like that. It represents the resistance. Resistance consume energy. That's why like the bounce in here go down to 0. If you have this, if you don't have the resistance, this one just going bounce up and down because energy is not lost. Delay definition, maybe I think, let's this. Okay. Delay definition, this one is the concept is simple. It's going from, you have you go from like it divide like the time interval between the input signal to the output signal at VDD equal to the input, the voltage of the signal equal to VDD over 2. So here's the input, right? Here's the output, which is this one is the inverter. So the input here go out like, because invert, you have this. So they based on like, like this one go from like a high to low, right? So they call like TP.HL. HL means a high to low, go from high to low. So you have this. And then similar, you have this one, say low to high. And we have this and this. And then they have the definition of the P is a propagation. So T propagation just take average of TP.HL to TP.LH. The reason for that is for the cell designer to evaluate if the cell is good or bad. Like let's say they design that I have that's why, okay, I come back to like why we need the balance between the P and N transistor. When the signal go from like a high to low like that, it means the N transistor is turn on, right? If it turn on with the higher current, so this one is a fast. Now, when you go from 0 to 1, it means the P transistor is turned on, which is like it's charged through the P transistor. If the P transistor is a high resistance, which is the current is small, then it will charge slowly like this. It will charge like this. So you can see that because it's charged like this, so you have a TP.HL and TP.LH is not balanced. So because of that, when you calculate, okay, that means like when it does like that, it will be some problem with like when you have the circuit. Okay, this one will cause a problem. Let's say the clock, right? For the clock, if you have this kind of thing, then the clock will like the clock is not one cell. It will be multiple cell, and they go like this, go like that. And it kind of like mess up the clock tree. So one of the requirement for the clock cell is they have the balance rising time and falling time. This called you have a TP.HL or like called like falling time. This one falling delay time. It's a falling delay time, and this one is a rising delay time. You have fall time here is a falling transition time. And rise time, the TR and TF here is a rise time here, rising transition time. So that's why I said like they have to design so that they have these two like a balance as possible. Yeah, falling propagation or falling like delay time, falling delay. So currently, no, not currently. This one, when it say like a 90 to 10%, this one is a very old days too. This one, because at the time, the reason we do 90 to 10% because in the old technology, the transition here is quite linear. So this thing is go here like that, is quite linear. So in between 90 to 10%, 10 to 90% here, they can pick that. The reason they don't put like 100%, right? Because if I like I just like zoom in for this, I zoom in for this portion, the whole thing like this, it will become like this, right? It will become like this. So if you take like if you take the slew time, transition time from 0 to 100%, so you see like this. So it doesn't reflect really the transition time. So they pick like here is a 90%, and here is a 10%. That's why they pick now 10 to 90%. So be faithful to that, the concept. going forward, because now the linear part of that is no longer 10 to 90%, but it go up to 20 to 80% and go up to like 30 to 70%. So you can see that like now they might not use like 30 to 70%, 10 to 90, but they will use a 30 to 70%, even 40 to 60%, because the portion of linear here is only like the small one. And actually now I think they have a new methodology to calculate the delay and the transition time by using the CCS model, which is I think that is used by Synopsys. We will introduce that in the chapter of STA, which is static timing analysis. Those things you need to understand. Those things. This is the basic concept you need to understand, but it's a simple concept, right? So it's not difficult to understand, but it's a basic, so that like later on we will go to this STA. So when they talk about that, charge up and discharge. So that's what we just talked. Charge up, that means that when you have 0 and 1 here, this P transistor turn on, it charged. So this one turn on, right? It's a short. The current charge from VDD to the load, which is this load is equivalent to the next stage plus the wire. And they make it simple so that only C load, but equivalent, there will be some resistance here. Basically, the circuit will be like that. Same thing. And you can see that because of resistance here and there, and then like the current when you charge it, if you have a 0 here, right, and you have a 0 ohm here, and you have 0 ohm here, so when you short like that, the circuit will go like this, regardless of the C, because it's 0 ohm. But because you have a resistance, it will go this way. You reduce the resistance, it go like faster. And similar, this one, discharge, right? It's a discharge here. If you have 0, it's like if there's 0 here, 0 ohm here, it is equivalent to like short circuit. So this one just like a discharge to 0 right away. So it will be like this. If you have this one with the resistance, it will charge like this. You reduce the resistance, it will charge faster, and you have that. Yeah, I think this one is what I just explained. I think a simple one. So you have like the CL. I think this one they miss the resistance. So but the L2, right? So I think R or C, that's the time constant. RC, they call that like the time constant. So this one will decide this one the thing is like it will design the rising time and the delay. The rising time and the delay, because if the rising time is like that, that means it measures from like VDD over 2. So I think if it's slower, then the delay will be even like slower. So we have that like the CL, the TR is proportional to CL. And is inversely proportional to beta, right? So beta, if it's fast, then you have this one. If this one is like a high, fast mean this one is a higher, then you have the less TR. The TR is a small, and so on. And this chart is equivalent. I think you can look at that. And yeah. Oh, okay. Again, come back to like so you have delay time here. Before I talk about the current, right? The current in proportional to like the only thing the designer can impact or design is only like the width. And you can see that now it's a delay time. You can see that again, the delay time is really proportional to width here. The mu here is mobility, right? So beta, this. So the only width here is what the designer can adjust to make the circuit like faster. Width here is in the denominator, right? Beta here is in the denominator. So you increase the width, that means you decrease the delay, which is increase the speed or the frequency. So these two things, one is the L is shorter, that's like the tech, you cannot do much. But the width is wider, then you have that design. But again, it's not your concern. This is the cell design concern. All right, I think we just in time for that. Next time we will really go into the signal integrity, the problem with the electronic signal in the layout. If you have any question, I think the class was recorded. Then if you can you can like access that to the website. I think Professor can put my last record into the website already, so you can like access to that. So, but if you have any question, you can send me email or you can ask me now. That's fine. Okay. So if anybody has any question, you can ask now. So we're waiting for 1 minute. If you don't have anything, you can send me later with the email. Okay. The question is, in slide 33, is it correct that the delay of NOT gate will impact the setup time? Yes. Yeah, let me go to the slide 33 so that like everybody can know what it is. Hold on, I think. Okay, can I go there? No, I think I have to this one. Yeah, okay. Yeah. Oh, okay, you have that. Okay, so the question is, okay, I'm sorry. I think I thought about something else. So is that like the yeah, let me delay of NOT gate will impact the setup time. No, the setup time here is no. There's nothing to do with the setup time here. The setup time here is related to the transistor, and also that's the transistor here. This one, yeah, it's not. The transistor here will impact the setup time. The transistor here. Because you can see that this one, right? This one is the NOT gate, and the NOT gate here is just that the reason of that to just latch the signal. When it goes here, it will latch. So somehow it has a little bit of like impact for the setup time, but not really. The one is dominant will be this transistor, because this one I think is, if this one is NOT gate here is a big one, so that it can switch fastly, right? It can switch very fast. Then whatever coming here, it will like go right away and then establish this the logic level right here. But the thing is here, if you have this one is like yeah, I think with this one, this really like the transistor here, if the resistance here is a high, so it's really like the current is a small here, the switching it will be like messy here. That's this one. This one impact is not that much. But this, yeah, I think it's in the circuit they do that. Like this one is not like this thing. Yeah, I think I see that. I see in the cell library they make these two because it's have the positive feedback here, right? So I see that like when they make these two gate, they make that not much. They make that it's just like a minimum gate length. Sorry, minimum width of transistor. They miss it. But this one will be like a higher gate, higher width, like a wider width for the transistor, so that they make it faster. Does that answer your question? Okay. So anything else? All right. Okay. Thank you, Professor Thịnh, and thank you, everybody. I think, again, if you have any questions, send me email. And then thank you, and see you next time. By the way, yeah, I think don't hesitate to ask me question. If you have a, I understand that like after the class, after like the class, you might not have the question right away. That's understandable. But if you have any question, don't hesitate to ask, because of the how you can like understand the class, and you can like move forward. Because if you have any like a hole in your foundation, it's difficult to move forward. For now, it's just like a two section, right? So it's not much. But going forward, don't hesitate to ask if you have any question. Okay. Thank you again, and see you next time. Right. Thanks, Dr. Professor. Bye-bye.